So hello everyone, let's start our second lab devoted to analog and digital integrated circuits. And today our purpose of our simulation is to demonstrate the characteristics and also operation of the spectrum analyzer as it applies to radio frequency communications. And in fact, the spectrum analyzer is one of the most essential testing instruments in the fields of communications. Okay, so let's design a sample circuit and see how it works. So we'll, as usual, need one resistor, one diode, and also a source of power and ground. Okay, so let's rotate it. So as a reminder, you can rotate elements by pressing Ctrl and R at the same time. Okay. And let's also add two instruments. So well-known oscilloscope we used in previous labs, and also new instrument, the spectrum analyzer. Okay, so let's set up some values. So mean square, let it be as it is, and let's change the frequency to 1 kilohertz. Okay. So let's connect our oscilloscope. So first of all, let's test if our circuit is working as it is supposed to work. Okay, let's go. Okay. So as you see, the scale is not appropriate, both for X and Y. Okay, so first of all, I'll pause it. So yeah, so here we see the channel A, so that is the signal which comes as an input to the diode. So it's a usual sinusoid. Yeah, is peak to peak value about 166 volts. So you can check that. In fact, it's the root mean square of this peak to peak value is about 112 and 120 volts. So now let's see what is the output signal. Okay. Yes. So that shows that our diode is not actually correctly, let's say, yeah, is not correctly connected, because we should have the opposite graphics as well. Yeah, so this part, this sinusoidal part, should be above the x-axis, and this straight part, which corresponds to the backward current, because of diode is not ideal, should be below the x-axis. So it's up to you to correct this. Well, yeah, but anyway, let's move. So now we will use our spectrum analyzer. Let's connect it here, and see the spectrum of the sine wave with root mean square 112 and frequency 1 kilohertz. Okay. Oh, yeah. Before we start, you should also set some parameters here. So the for spectrum analyzer. So first of all, let's use the linear scale. So probably amplitude will be above the default value. So start and end value now we should set. So the frequency of our initial sine wave is 1 kilohertz. So let's start with it. And end value, let it be, for example, 5 kilohertz. Okay, let's set it. Okay, here we go. Okay, so that's actually what we see here is this one peak. Okay, let's change a bit because let's start from 0. Yeah, from 0 it could be seen here. Yeah, so so as you see, we have this peak in spectrum exactly at 1 kilohertz. At least it should be. Yeah, but because of this not ideal element, we have this peak not exactly at 1 kilohertz as we should have here, because the only spectral part we have actually this sine wave. So we should have only this one peak at exactly at 1 kilohertz. Anyway, we have it, and and as you see, we don't have any other peaks, so no other spectrum components are present at this point. So when this sine wave enters diode, we have only one spectrum component exactly at 1 kilohertz. And now let's use one more spectrum analyzer, and let's see what's the signal here. Yeah, let's set it. Okay, so we start at 0. Oh, at 0 and ends at 5. Okay, enter. Okay. So as a reminder, this spectrum analyzer shows the signal as in center of the diode, so the input signal, and the spectrum analyzer will show the output signal when it outputs from diode. Yeah, let's go. So here you can see some interesting facts. Yeah, so we have this peak exactly as we had it here. So this component is which was present here is also here, but we can see also some other peaks. Yeah, so here, also here, and so on. But as you can see, the amplitude of these peaks falls. That's in connection of what I was teaching you during the last lecture when we talk about Fourier transform and also the spectrum of the signal. So the first component in each spectrum had the highest amplitude, and then frequency get bigger, the amplitude falls. Yeah, actually we can try to as I want to show you how this actually is see here is peak, here, here, and now the spectrum begins to oscillate. Yeah, but actually this diode is not a linear component, and it would be used in real circuits to solve some class of problems. For example, you are given a scene-like source of power, for example, and scene frequency is 1 kilohertz. So you are given also a diode and maybe a filter, and you are asked to make all needed, let's say, manipulations to receive a scene wave, but the frequency of it should be not 1 kilohertz but 2 kilohertz. So using a diode, one diode, and also a filter, like parallel filter, which includes this inductor and conductor, you can easily do that. So, for example, as you can see here, we have at least two spectrum components, one at 1 kilohertz and the second one at 2 point something. So how this task should be solved? So we should use two filters which cut out this component and also all these components, leaving just this one component. Yeah, and actually your task would be to do that. Yeah, so the first one is correct this. So we should so first of all try to answer the question, why do we have such funny oscillogram? So as you know, it should be the opposite. So this scene part should be above and this part should be below. So why so? Why we have such an effect? Yeah, it's somehow related to the effect we had in the first lab with this voltmeter. Yeah, and then we had a negative voltage. And also your second task is, of course, to repeat this design. So try to resimulate it. And also your third task, but actually this is an optional task, but as a reminder, if you want to have an opportunity to receive a 10 as your final mark, you should do all optional tasks for all labs. And so the third, and it is optional task, is to do what I was explaining to you a few minutes ago. So you will be given a sinusoidal source of voltage with 1 kilohertz, and you should use diodes. One diode probably will be enough, and also a filter which consists of conductors and inductor. So you should somehow design this circuit to get a sine wave as an output, but the frequency of it should be 2 times greater than we have now. So not 1 kilohertz but 2 kilohertz. So the submission deadline, as usual, is till the next lab. So you have 2 weeks to complete it. So by the end of next week, so by next weekend, I'll also send you a sample report, so how it should look like. Also for an optional part, there will be some questions listed and some hints how this could be done. And we also will talk about these filters during our next lecture. Okay, so we this at home, you can do this in the class as you wish. So as usual, if you have any questions, concerns, comments, you know how to contact me. Please email to me. You can also ask your questions during our lectures. So at this time moment, I think we are done for today. So thanks for watching and have a nice day. I'm waiting for your report. Bye bye.